Good morning and welcome to the keynote session. It's my great pleasure to introduce the keynote speaker, Salil Kanhere. He's an associate professor at University of New South Wales, Sydney, with conjoint appointments at NICTA and IITUA, Singapore. Prior to that, he received his master's and PhD degrees from Drexel University in Philadelphia, and his research interests are in pervasive computing, Internet of Things, sensor networks, crowdsourcing, security and privacy. He has written over 150 papers, presented many tutorials and keynotes. As we all know, he serves in many organization committees, not just at LCN and Census, but also PERCOM, Mobisis, WOWMAM, and many other conferences. He was a Humboldt Fellow in 2014, and more than any of that, he's a great person. So it's my pleasure to introduce Salil Kanhere.
Thank you. Thanks so much, Anurag, for the kind words. Before we start, a special thanks to Matthew here. He's been working very hard, especially this morning. He has to do 3 talks. Okay, so thanks, and good to see all of you here and not out there. It's very gorgeous outside. I just had a quick look. So thanks again for staying back. So this work was, I should acknowledge all my co-authors without whom this work wouldn't have been possible. So this work is actually part of a project I'm doing with I2R, the Institute for Infocom Research in Singapore, where we are looking at participatory sensing and particularly the issues of incentives, trust, and privacy. Okay, so just a quick primer. What exactly is crowdsourcing, right? So it's actually, if you look at the dictionary, by the way, this is now an official word in the Oxford Dictionary. So it's kind of a combination of this term outsourcing to the crowd, right? So you're using the crowd to do sort of some tasks, you're getting the help of a large group of people, and the way you do this is typically over the internet, because the internet allows you very easily to reach a large group of people. And this, I mean, the idea was there. The actual term was coined by Jeff Howey in an article, I think around 2006 in Wired, where he had this article titled The Rise of Crowdsourcing. And I guess around the same time, there was a very nice book called Wisdom of Crowds that came about. It's a very nice read. I would recommend all of you interested to have a read if you have. So I thought, okay, let's first step back and look at history, right? So where has this idea actually been used? Now, if you go back in time, you'll actually see several examples of crowdsourcing that have been used. So I just picked a few. So dating back to the 1700s, right? The British monarchy, I guess, at that time, not really a government, I don't think. They had this problem. They were sending out ships trying to conquer different parts of the world, right? So one of the issues they had was when the ships went out, they could easily figure out the latitude, but figuring out the longitude was a big problem. So they set up a prize, which was quite substantial, £20,000 back then, for people who could come up with solutions. And there are actually examples where people have come up with nice solutions and they've been able to share part of this bounty. If you go back to the Oxford Dictionary, actually, the first edition of the Oxford Dictionary employed crowdsourcing. So they actually used 800 people to sort of catalog some of these words in order to create this first edition, first version. Then if you look to the 1900s, there are again several examples. I picked this one from Paris, where they were doing a sort of photography competition, asking people to contribute pictures of the architecture and how the architecture of Paris has evolved. Since I'm from India and I like Bollywood movies, I think this is a nice example from the 70s. So this is actually the first crowd-funded film. This was a film based on the milk cooperative movement in India, and this was financed by 500,000 farmers, each paying 2 rupees. It's not a substantial amount, you might think, but back then, for these poor farmers, it was still significant. And then in the 80s, that's when crowdsourcing really took off, right? You've all heard of work by Richard Stallman and the GNU project, and then of course Linux, open source. So that all sort of came about in the 80s and 90s. Right? 2000s, again, you have several examples, Wikipedia, which all of us use, Mechanical Turk, Stack Overflow. A lot of my students keep asking questions there. I often troll Stack Overflow to see if they're asking people to solve my assignments. TaskRabbit and so on. And then at the turn of the century, really, mobile took off, right? So as we all know, we've all got these fantastic smartphones, and if you look under the hood, there's a bunch of sensors actually in these smartphones, right? You have sensors to detect your motion, you have sensors to detect your location, what you speak, what you see, the temperature around you. So there's a bunch of these sensors integrated in this nice small compact device that we all carry. So it's a very nice platform to actually collect data from our surroundings, right? And in a sense, crowdsource all this data, or what's also called crowdsensing or participatory sensing or urban sensing. You've all heard these kind of terms thrown around. Right? Now, why is that possible? Well, you have these sensors, you have good connectivity pretty much anywhere you go. You have a nice application distribution system, so you can develop these nice apps and beam them across multiple devices. There's a good backend, so you can collect all this data, do a lot of data crunching in the cloud. And of course, it scales enormously, right? Because everyone has a phone, there are billions of people with phones around. So even if a small fraction contribute, you can still get reasonably meaningful data. So perhaps I'll spend just a few minutes touching on what kind of applications are actually out there, right? This crowdsourcing has been sort of, I think the first work in mobile crowdsourcing came about late 2006, so it's over 10 years that people have been working on this technology, right? So what sort of things can we do? Well, we can easily sense a lot of things happening in our environment. So this is some work we did a few years back where we were collecting information about noise profile in cities. Right? There's a lot of noise in urban environments, traffic, construction, airplanes, and so on. Right? And so city councils want to sort of find out what are the noisy hotspots. Now you could certainly go and deploy static sensors, but who's going to pay for that? Right? When you have people walking around, you could install a noise measurement app. You could get a few people to contribute and build a reasonably detailed noise map. So that was the idea. A colleague of mine sort of looked at it from a different angle. He was saying, okay, can we use the same idea to monitor the air pollution? So he built this small box that you see up there, got it manufactured in China, stuck it on a few cars. It had a Bluetooth interface which could talk to the phone, and then you could upload all this air pollution data. There's a bunch of sensors in that box, carbon monoxide, ozone, and so on. Right? So you could get a very nice view of air pollution levels in the city. As you see there, some data from Sydney. There are a bunch of such apps out there. There's an app called Weather Signal, which can use the temperature and humidity sensor in your phone. So if you install this app, you can get some information about the temperature and weather in different parts of the city. So this, I just pulled this a few days ago. This is from our campus in UNSW. Waze. How many of you actually use Waze? Anyone here? Okay, there are a few people here using Waze, so that's great. So this is actually all crowdsourced, right, as you all know. This data is collected, GPS data is collected from that app, sent back to the backend, and you can report a bunch of interesting things. You can report if there's a speed radar somewhere, you can report gas prices. So you can crowdsource a lot of information and overlay it on the road network. Right? There are applications in transport. So this is an app called Move It, where you can sort of update real-time information about public transport. So if you're traveling on a train, you have this app running, it will sort of send real-time information of where this train is, and then it can be useful for others who are waiting for this train and so on. Right? So you can get real-time data. This is an example of ride sharing. Right? So let's say you're driving from, say, Clearwater to Miami today, right? And you have vacant space in your car. So hey, why not get $10 by giving a ride to someone else? Right? So this is an app that allows you to do that, where you can actually get some money for sharing your car. There are applications which crowdsource photos. So this is kind of like Street View, but this is open source. This is doing this over open Street View. Open Street View. You can also use it to collect data about pricing. A lot of brick and mortar stores, they sell goods for different prices, right? And this might not be easily available online. So you could crowdsource this data from people who are actually making those purchases. So we did one example of this by looking at fuel or petrol, as we call that in the US, or gas, right? We call it gas. So when you're driving past a gas station, if you mount your camera facing outwards, it will automatically take pictures of the billboard, and then you can do some image processing to extract out these prices and upload it automatically to a backend. This can be shared amongst other people. Some other examples. This is a very nice project, Open Signal. They crowdsource network measurements, so you can build nice maps like this of 3G coverage, 4G coverage in cities. This one is sort of crowdsourcing connections. FireChat, if you've been following some of these crises in Syria, Egypt, and so on, they've actually been using this to establish connectivity among these people, because there are problems with the cellular network which are heavily censored, right? Or say you're in a stadium, you're at a concert, and you just can't connect to the 3G network. You can establish an ad hoc connection amongst people. There are nice examples where you can use this to volunteer. So, Be My Eyes. If you have 5-10 minutes of spare time, I would strongly encourage you to participate in this. It's a very nice initiative where you can help blind people, right? So you see here a picture where you can sort of lend your eyes to the blind through video chat. It doesn't take a lot of time. I've done this a bunch of times. Citizen sensing, right? So the idea of collecting data to help others. This is it's not perhaps that useful, but just a nice example, right? So finding a public restroom, right? So if you go to a restroom, you've used the restroom and you can rate sort of. If you like it, you say sit. If you don't like it, you say squat. So these are some restrooms here in the area. So if you go out now on the beach, and if you need to go urgently to one, please use this app. Okay. Go to the green ones, not the red ones. Okay. Those are the squats. Okay, all this is fine. I mean, I've given you nice examples, right? Great. But what's the problem, right? Well, if you look at a lot of these, there is very little data, right? If you go back here, I mean, I had to sort of zoom in and find a place where there was actually sufficient contributions, right? The problem is all this is hunky-dory, but where is the data? Who's giving you the data, right? And this was a question that was sort of asked every time I gave talks. I mean, I've been working in this area for a few years now, and in every talk, I always got the question, what are the incentives? Why are people going to contribute, right? So I sort of bit the bullet last year, and we started looking at this whole issue of incentives, right? I mean, there's some cost involved here, right? It's time, it's effort, it's bandwidth, right? Privacy, I mean, people are worried about their data, which is quite understandable, right? I mean, if I give you my data, what are the chances that you're going to use it to track me and see what I'm doing and stuff like that? So there's always this question, right? What could I gain from this, and why should I contribute? So we clearly need some incentives to do that. And if you look at how you could incentivize people, you can kind of look at two ways, right? So one is sort of the intrinsic incentive, or this is sort of something that comes from pure altruism, right? So if I feel that I should contribute, I don't care if I'm getting anything out of it. I do it just for the joy, right? I feel good, right? So that's what we call intrinsic incentives. And on the other hand, you have, of course, extrinsic incentives, right? Where you kind of set up a monetary incentive where you actually pay people. And of course, both work in certain instances, but typically to get a wider reach, you do need to look at this option. That only works in limited cases. So we started looking at this, and what I'm going to do is I'm going to present two pieces of work that we've been doing very recently. So this first piece of work looks at what we call all-pay contests or all-pay auctions. So this work was presented in Mass last year, and we just recently have a journal version as well. Right. So this is an auction-based framework based on money, and as it says there, Tom Cruise nicely says, "Show me the money." Right. Okay, so just a quick primer on auctions, right? So how do auctions work? Now I've set this up in the context of crowdsourcing, but clearly, typically, the auctioneer is selling something. Right? Here I've twisted it around a little bit, and I've said, okay, I have $10 to pay you. How many samples are you willing to give me? Right? So you have a bunch of, so this is essentially the bidding stage of a bunch of bidders, and each bidder can say, okay, I'll give you X, I'll give you Y, right, so on. And then the auctioneer can say, okay, you win, send me the data. This person would send him the data, and then he would get the monetary reward. So that's the standard model for auctions. You have two stages, bidding and risk contribution. The other option is what are called all payout auctions, right? So in here we kind of compress those two stages into just one stage. And again, say the crowdsourcer says, okay, $10 for your samples. Now in this model, the auctioneer or the contestants directly send their samples. So in a sense, the samples themselves become the bid. Right? And then based on certain criteria, say the number of samples or the quality of samples, the auctioneer can say, okay, you win, here are your dollars. So this is what we call all-pay auctions. Now you might say, okay, why all-pay auctions? They might not seem a bit intuitive, right? I mean, you're kind of asking people to give data, but only one of them is actually going to win. Well, if you think about it, this is in a way a natural model for some crowdsourcing tasks, not all, I should qualify that. Because the effort, right, if you look at a crowdsourcing task, often the effort is actually already sunk in, right, and it's kind of irrevocable. You might collect data already, and then it's like, okay, instead of throwing away the data, might as well contribute and hope that you can win. So that's the idea here. The other good thing is it eliminates the risk of non-fulfillment, right? So in traditional auctions, you kind of take the person's word, right? So okay, I say I give you 10 samples. How are you going to police it, right? I mean, you can, but it becomes too much effort for the auctioneer. Try to police and make sure that the bids are actually fulfilled, right? So this simplifies the process because it's just a one-shot thing. You just do it one time and that's it. Okay, now this is traditionally these are all auctions, but I've set this up as contests, right? So I just want to sort of make that inverse thing clear. Okay, so what is exactly new here? No question.
Yes, actually, why not to give some, because you already get the information, why not to divide this amount and rather than have one winner to have multiple winners, everyone get this share proportional to the data that is.
Yeah, that's a good point, and that is something that we are looking at in future work. So here we are sort of just saying we are after the best data. We want to motivate people to give us the best data. Right? Having multiple prize winners is something we look at in the future. As you will see, this model is already very involved to begin with, so we wanted to start off with something simple.
So what is the mathematical model for that?
Yeah, I'll get to that. I have all this here. So, yeah, so that's what I'm saying, leading to. So what are the differences with the prior work, right? So prior work has typically assumed a homogeneous setting in which they assume that all players are equal, right? So they're kind of statistically equal or deterministically equal, which leads to what's called symmetric equilibrium, right? So everyone is more or less equal. However, if you look at again, most crowdsourcing scenarios, the participants will not be equal. How do we measure equality? Well, it depends on the task, right? So it depends on the ability. So say in an academic setting, you would trust perhaps academic more than a PhD student, right? I hope so, though sometimes it's always the other way around. PhD students kind of know more than the academics, but let's say we don't consider that, right? So that's what we call abilities, right? So each agent can have different abilities. Moreover, beliefs are also important, right? So when you're competing, you kind of assume something about the other competitors, right? You assume their nature, you assume how they would behave. Typically, if you look at a game theoretic setting, you kind of have some assumptions about how the other people behave, and then you act rationally based on that. So what we assume is actually an incomplete setting. So we assume that you have some probabilistic knowledge, but never complete information about the other players in this. And again, this clearly captures a fairly realistic setting. So this essentially is our mathematical framework. Okay. Now, so a quick summary of contributions. So this work is the first work that has looked at this heterogeneous setting and the use of all-pay contests. So what we do here is we design an incentive mechanism and we show how to optimize this so that you can optimize the profit for the crowdsourcing, so the person who's actually setting up the campaign. Now this was a complete something that sort of just came out of the analysis. We didn't have this in mind when we started. So we actually discovered a property which we call strategic anonymity, strategic autonomy. And here we show that even if this is a heterogeneous contest, right, heterogeneous model, we show that the agents actually behave as if they are in a homogeneous one. Now I'll make that clear, what are the implications a little bit. And then we present an example of how you can deal with different crowdsources, because each person who sets up a crowdsourcing campaign may be different, and in fact the same person may evolve with time. Right? His valuation of the data may evolve with time. And then we have some performance evaluation. So let's now get into some of the nitty-gritty. Okay. So this is our model. We want to crowdsource certain effort from n agents who could all be different and who have different beliefs. And the goal is to maximize the revenue. Right? So you have, the goal is to maximize the effort minus the cost. Right? So everyone contributes, which is the effort, and then the crowdsource has to pay, which is the cost. Now what do we mean by effort? So this could be anything. It's a fairly general model. So it could just be the quantity of data, it could be the quality, in other words the best data, or it could be a combination. So our model is fairly general and you can tweak that as you wish. The agents, we assume they are associated with a certain type. So we assume this VI is certain way to typify the agents. And this could depend again on various things, right? So it could depend on, say, qualifications, it could depend on age, whatever your setting may be. And this is private, so only I typically know my type. Okay? I don't know your type. We assume that the agent has some belief, okay, about the other players. Now you might say, okay, how do you develop this belief? Well, often in these crowdsourcing applications, there's always this interface where you can see the type of people involved, what sort of data they're contributing, or there might be some underlying social interaction happening. Right? So you could perhaps glean some of that data from social interaction, or there could be just some public information out there. Right? So this is what's called an incomplete information setting, and this constitutes an asymmetric Bayesian game. The effort is the actual bid, which is VI in this case. So that's the actual bid. Whatever you do, whatever effort you put in is your bid. So that's the model that you see there. And the crowdsourcer, or what's called the principal, he sets up a price tuple. Now this is unique. In past research, typically the price tuple is just constant. Okay, there's just one fixed price tuple. So what we said was, okay, why not have the price to be proportional to the winner's bid? Right? So if you bid more, right, you get a higher reward. So that's the idea. And this is self-adjusting, and this is known to all workers. So assume that at the start of the campaign we publish this. Okay, these are the prices you're going to get. Okay, so now the objective function, both for the agent and the principal. So the agent wishes to maximize his utility, which is QI is the winning probability. So what's the chance of I winning? This is something again new that we've introduced, which is the valuation of the price, right? So this means, okay, if you get the price, what value do you assess assigned to this price. Right? Now, traditionally, in classic auctions, this is actually fixed. So, which means my valuation of the price is the same as, say, Anura's as Olivia's. Right? Now, if you think about it, you could kind of perceive this could be different. Right? So, imagine the price is, I don't know, research amount, say a research quantum. Right? Let's say this is based on publication. Now, the way I value my, say I get $1,000, my valuation might be very different from Anura or say Olivia's of that $1,000. Right? So one example could be, as you see there, this valuation could be just proportional to VI, which is the type of the agent. So a stronger agent values the price more, right, compared to a weaker agent. That's the idea. I mean, again, that's fairly general. You can set that up as you wish. This is a fairly general model. And then this, what you subtract is the cost incurred, right? So what cost is incurred in actually collecting the data. Now this is again proportional to the bid, because that's essentially the effort, and the type of agent. Because a weaker agent has to put in more effort to kind of generate the same data as compared to a stronger agent. Okay, now the principal, which is the crowdsourcer who sets up the campaign, is profit seeking. So his goal is to maximize the profit, which is essentially the total effort. Now again, in this equation we've set it up as a combination of all the bids, but this is fairly general. You could just set it up as the best bid if you're looking for, say, a crowdsourcing campaign where you're after a solution rather than just a collection of data. So that's the effort, sum of the effort. And then we subtract the cost, right? the amount that the principal has to pay out. And again here, we set this up as a value function. So this lambda here is the valuation of the price. So if I'm a crowdsourcer, how much do I value a certain amount of money? Right? How much do I value, say, $10 as opposed to, say, Igalia, who might value $10 differently than me. Right? So that takes care of the different types of crowdsources. And then ZW is the actual price that's paid to the winner. W is the winner. Okay. Okay, I know it's very late in the conference. Okay, you're all waiting for lunch. You clearly do not want to see theorems and proofs here. So please feel free to read our paper. I'm not going to show you any theorems and proofs. I'm just going to show you the final result. Right? So this is the final key result that we have. So this is the effort. So this is the optimal effort that must be put in order to win. Okay. Up there you see the price tuple that we've set up. That's the optimal price tuple that will result in the maximum profit, which is shown here. And I know this is all equations. It's clearly not possible to absorb this, so let's not waste time.
You have a typo in equation 3, by the way. It should be minus there and just a joke.
Okay, I was surprised how you could pick that up so quickly. Okay, so let me just sort of give you some intuition and point out some key findings. Right? So this was something that we discovered which we didn't actually have in mind. So this is what we call strategy autonomy. Right? I kind of described this earlier. So if you look at a traditional game, right, and you're talking of rational agents, as an agent you typically have some perception of what the other agents, how they might behave, and based on that perception, you might think, okay, this guy is going to behave this way, so let me adjust my bid based on what I think he's going to do. Right? That's what it sort of is the norm in a traditional game setting. However, what we found here in this particular setting is that the strategy that you use is actually completely independent of how the belief that you have of the other agents. And this is kind of captured in, again, I don't want to throw out equations, but if you look at equation 8, you'll see that it only depends on I. Because you don't really need to have any information about the belief of the other agents. So what this means is you're kind of behaving autonomously as if that you were part of a symmetric equilibrium. Right? So this is very sort of counterintuitive, and it's certainly a new property that we discovered. Now you might say, okay, why does this happen? Well, the reason for this is because of the price tuple that we've introduced. This price tuple actually absorbs these differences amongst the beliefs, amongst the different types of agents. Right? And again, I'm not going to go back to the equation, we can look that up. Okay, you might say, okay, great, but what do I gain? Right?
Yeah, just a second. There are some extent, but this, basically this is everything is dependent. There is the issue that, what is your probability that you will win? This is something. And it's also dependent on the probability that other experience and believe, because this is some sort of relate. Again, this is my sense that actually there's some dependency here. Because there is a game here.
Yes, there is some dependency, but that gets captured in the way we have set up that price tuple. So certainly, yes, there is a dependency, but the way we set up this price tuple kind of takes care of that. Right? If you look at the price tuple, that actually factors in those beliefs of the other. Okay, great, but what are the practical implications? Right? So firstly, if you look at the strategy that a player has to play out, you will see that it is actually order of 1. Again, I won't go back to the equation, but if you go back to equation 1, you will see it only depends on the properties of that particular agent. Right? So this is order of 1. If you contrast that with classic options, which is captured in this equation, you will see that you have to consider your belief on other agents as well. Right? So that's order of n. So what that means is, if you're trying to implement this on smartphones or smart devices, it's going to be much easier. Right? You don't have, and typically in crowdsourcing setting, you'll have hundreds of agents, thousands of agents. Right? So clearly, this is quite important to have an efficient strategy. Second, it also increases the crowdsourcing revenue. Right? So this is what is known as effort reservation. Right? So let me give you an example. Have you seen Usain Bolt race in one? If you look at some of these races from last year, right, you'll see as he approaches the end, he's sort of just showboating, right, turning around, looking at the other, right, and he's not putting in all his effort to finish the actual race. Right? Why? Because he knows that he's already ahead of the others. Right? So he's kind of saving some of his effort. Right? And not putting in all his effort, which he perhaps would do, say, in an Olympic final. Right? So this is what happens when the price is fixed, because there's a fixed price, right? And you know that, okay, this other agent is not as strong as me, so I can sort of, if I know I'm winning, I'm going to just take it a bit easy. Right? Whereas in our setting, because the price is actually dependent on the effort that you put in, you have some motivation to go the distance, right? Put in all that effort, so that because you know you're going to gain out of that. So that's what we achieved here. The third implication is it enhances system scalability, right? Again, move here. Okay, board standing in one. Okay, so if you look at traditional economics, right, there's a universal law that says, okay, as you increase the resources, right, you'll sort of start to taper off. The actual gain you get out of that is going to start to taper off. Okay. So this is very common, it's kind of well known. And as you'll see later in our results, we actually show that with strategic economy, this goes away and we can actually get a linear benefit. So I'll show that to you in some of the results which are coming up now. Okay, so we've done again a bunch of evaluations. We've actually done three set of evaluations. I'm only going to present to you 2 sets and only a few results, just to sort of make some of the points clear. So in this case, the first setting is where we only have 2 agents. In this second setting is when we have n agents. Okay? And by simulations here, I mean this is all numerical. Okay, I know this is all theoretical work, but to get this going, we have to have a solid theory. And now, currently, we are looking at how to sort of implement this in a real system and do some proper simulations. I know there's going to be a question about that later anyway, but I'm just sort of making it clear out here. Okay, so we have the optimal strategy, which is our strategy called OPT, which is asymmetric all payout. Then we have a fixed setting, which is a fixed price option. It's still asymmetric, but the price is fixed, unlike ours, right, where the price depends on the bid. And then we have two symmetric settings. I should mention that the two agents that we select have the following belief, as you see there. And statistically, agent 1 is always stronger than agent 2. Right? And so in the fixed price, which is the sim 1, we assume that both agents are strong. In sim 2, we assume both agents are weak. Okay? So that's our setting.
Oh, sorry, what is the meaning of strong and weak?
Yeah, so that depends on your ability. So based on the crowdsourcing campaign, right? Based on your ability to contribute data, this VI captures essentially how good you are at that task. So let's say it's photography, some campaign based on photography. If you're a professional photographer, you would have a higher VI. If it's me who takes crappy photos, I'll have a lower VI. Okay, so first let's look at the profit ranking. Right? So in this case, that's the ranking that you see up there. Sim 2 is the worst, Opt is the best, which is this black line that you see. And here you have the principal's valuation, right? So the campaign, how he values the actual price. Now, of course, as his valuation increases, the profit goes down because he has to pay more. Right? The more he pays, of course, his profit goes down. But you'll notice that in our case, if you look at these two, you're actually going into deficit. You're not making profit. Right? In fact, even this one goes down, but OPT, we never reach a situation where you're actually losing money. Right? So that's one good thing. Now let's look at some other comparisons. First, let's focus on these two. Right? So Sim 2 is worse because, of course, it has two weak agents. Sim 1 is better because it has strong agents, and Fix is sort of somewhere in the middle because we have a combination. But you'll notice that this is actually not halfway between these two. Right? You would expect this to be halfway because it's a combination. In fact, this is even less than half of the blue line. Okay? So why is that the case? That goes back to that example I told you, the effort reservation. Right? So the strongest bidder is actually reserving his effort and not giving it his all. Right? And you see that in here. This is in the fixed option, this is the fixed option setting, this is agent 1. And then if you look at the symmetric case, right, that's agent 1. So you see that he's clearly not putting in sufficient effort because he knows he's going to win. Right? So that's capturing that result. What you'll also notice is agent 2 is actually exerting slightly more effort. Right? So going back to that Usain Bolt example, the person who's second, if he knows that Usain Bolt is sort of going to decelerate towards the end, right, he might give it that extra effort just to hope that he might sort of be able to beat Usain Bolt. So that's exactly what you see here. With agent 2 is trying to sort of perform slightly better, but in the end, if you look at the sum, it still falls short. So the key takeaway is that the stronger agents matter more. Right? So which means as a crowdsourcer, it is more productive for you to focus on incentivizing stronger agents. Oh, sorry. Okay, so now let's look at our scheme. Okay? Now again, you might say, okay, in the symmetric setting, you have two strong agents. Right? In our setting, remember, there's a one strong agent, one weak agent. So two strong agents should be better than what we have. So why is that the case, right? Why can our scheme do better, our setting do better? Well, this is because the equilibrium strategy induces higher effort, right? Why, sorry? Yeah, this is because the way we have set up the price tuple, right? It's actually going to motivate this second agent a little more. So here, you'll notice this is the weaker agent and this is the stronger agent, right? So the way our price tuple is set up, it's going to give more incentive to the weaker agent, trying to push him, trying to get him to sort of do that extra bit. right, in order to compete and win against the agent 1. So the way we set this up, we are kind of creating a very fierce competition amongst all the agents. Right? And if the agents are sort of fairly close in their ability, it creates a very strong competition, and you get sort of a strong push towards the end where you can exert very nice bids from all these agents. So that's kind of the idea there.
But if there is a major gap between them, then
Sorry?
If there is a major gap between the agents, then you cannot do
that is perfectly true. So if you have a very weak agent competing and then you have a clear winner, yes, this is not going to be as useful, certainly. Okay, now the second result, okay, how do we utilize this property of diminishing returns, right, as you add the number of agents. So this is where we look at scalability, so we consider multiple agents, right, and we compare the optimal scheme and the fixed scheme, and you very clearly see the fixed scheme tapers off, whereas the optimal scheme is linear. Now, why this is because again due to the strategy autonomy. I won't get into these numbers, but if you do the math, you clearly see our scheme is, results in the linear curve. Right. So just a quick summary. Okay, where we are. So this is the first work that looks at this heterogeneous setting using all pay contest. We show how you can set up an incentive scheme, and we show how you can optimize this, right, to get the maximum reward. We come up with this unusual discovery of strategy of autonomy. I don't know why I keep saying autonomy. And this has practical implications because it allows you to implement this efficiently. It allows you to maximize the crowdsourcing revenue, and it is very scalable. Right? So I'll leave this first part like that. Are there any questions on the first part?
Yeah. I think there is something which is misleading or inaccurate in your model, obviously. And the problem is the following: we assume that actually the strong agent and is somehow some of the expectation of the strong agent versus the weak agent. So the strong agent for you is actually you get example as a photographer. It's actually it's much easier for him to produce good pictures, but actually his expectation is to have much higher reward.
Sure.
As well. So actually, if you have something like small amount of money, you may not have strong agent at all because you have just small amount of money. They were not willing to work for such a small amount of money. While weak agent, they want to get something, they will do the job.
Yeah, so that may be true, but I guess you could structure the price in a way where you kind of still strike this balance, right? So if you give up, as you say, very poor reward, looking for the maximum profit, I agree that it might not motivate the stronger agents, right? But if you move a little bit further and sort of start increasing your price that you're willing to pay, right, you can still have sufficient sort of contest between these stronger agents. I mean, that's the reason we show sort of going back to some of these graphs, we're looking at all types of agents. Right. So as you said, here, there's not much benefit, but once you start moving further up here, you see greater benefits. Okay, so just looking at the clock, making sure we're on time. So now I'll talk about some very recent work. This is a different approach, slightly different approach, using this idea of tune-up contest. This was presented at InfoComm earlier this year. Right. So yeah, maybe I've convinced you what is good about options. Right. Now I'll sort of take a different view and tell you a bit about what's not so good about options. Right. So you have to be, if you kind of go back to the previous work, you have to be the strongest person. Right. You have to be the strongest guy in order to win. That is very clear, right? When you see it. So the best winner wins with probability 1, others always lose, for sure. Now, what this means is people may actually not contribute, right? If they have some insider information that, okay, this other group of people is always going to win, they're much better than me, then you're going to say, okay, why should I contribute? Right? I know that I'm not going to win. let me just not contribute data in this case. And this may not be desirable, particularly for applications where you're looking for things like coverage. Right? If you have a campaign where you're looking for the best solution, this is not an issue because you really want the best solution to a particular problem. Right? However, if you're looking for data that covers, say, something that's diverse or over a large area, then that may not be suitable. Right? So you want to sort of look at another way to set this up. And so that's where we started looking at this idea of lottery. Right? So if you look at a lottery, you always have a chance to win, right? No matter what, how weak you are. Right? So this is a pioneering work by Gordon Tulloch from George Mason. That's where James comes from, in the back. Right? He actually passed away last year, I think, if I remember correctly. Okay, so the idea here is it's imperfectly discriminating in that every player will have some probability to win, right? Based on what we call a contest success function, and this is user friendly, right? And there are a lot of examples of this, as you see, right? With lotteries, why do people buy lottery tickets? Because they always think they can win, no matter what, right? And there are lotteries in pretty much every country in the world. Right? So what are the differences? Well, in all pay contests, we are creating this strong, fierce competition amongst, say, perhaps a small number of very strong players. Okay? In Tulloch contests, it's a kind of different setting where we are trying to sort of create competition amongst perhaps medium players, medium ability players, but a much larger number. So that's the contrast here. So all pay options are more suitable for solution-based problems where you're really looking for the best solution or the best quality data, whereas Tulloch contests may be more beneficial, as I said, for coverage and things like that. Right? Of course, there's no clear winner in terms of revenue, and this has been shown in past research. Okay? If you go back and look at some papers, they've looked at this distinction and they've shown it doesn't mean that one is better in terms of the final profit, it's just that they're what we call horses for courses. Right? Okay, so the summary here is, this is the first attempt at using Tulloch contests in this setting. And as before, we create an incentive mechanism and we show how we can optimize this, okay, by provisioning the price function. And just like the previous work, the focus here is on efficiency. We want this to be efficient so that you can implement it on smart devices. What we also do is, in order to benchmark this scheme, we found that there is no actual real solution to optimal fixed price Tulloch contest. So what we do in this paper is we also derive this so that we can compare against the strongest benchmark, and we show that our scheme is better than this strongest benchmark. And we also introduce this notion of the crowdsourcer's valuation of the user contribution. Right? So how much as a crowdsourcer do I value your data? Okay, and we show that this can also have a positive effect on the performance. So again, I'll keep the MAC to a minimum, okay, I promise. So this is the contest success function. Or maybe I'll just skip this because I have this in one of the later slides. Okay, so the contest design, right? So we want to maximize the revenue for the crowdsourcer. And if you look at current approaches, this is based on either a single prize, multiple prizes, or what are called biased players. But what we suggest here is to set up the price as a function, right? So the price will again be based on the actual effort, and this creates, in a sense, we are looking at a two-tier incentive, right? The first tier is the standard one that you want to win, but as before, the second tier is you want to amplify the price, right? So you want to give it your best, hoping that you'll get the maximum reward. Now the crowdsourcer's objective is then to maximize the revenue, which now becomes the maximum profit, maximizing the profit minus the cost, which is not fixed. That's the difference, right? In the previous work, this cost is actually fixed. In our case, the cost is not fixed. So this is the contest model. That's the probability that you win, and this is based on your effort divided by everyone else's effort. You have a price function, which is dependent on the contribution, and as before, this is known to all. So this is announced at the start of the campaign. The player playoff is the probability that you win times this price function minus the cost incurred, and the cost would depend on, again, the agent. Right? So one agent would have to put in more effort, say, to generate a particular bid than another. So this CI kind of takes care of that. And then the profit is the summation of that cost. And you'll notice there's a V there, a multiplier, which is the organizer's valuation of the user effort. So this is something new that we've introduced. In past research, this is just one. Right? So they don't sort of assume that a crowdsourcer may assign a different value to the total effort. So the goal here is for the player to maximize that and for the organizer to maximize this. Okay. Now unfortunately this is all very difficult to analyze, but luckily we managed to come up with a simple and closed form solution to this. And again, I'll direct you to the paper. I'm not going to go over all the math. These are the main results. I'm not even going to spend more time on this. So we're running out of time. Again, so what are the properties here? So the first is, since it's a closed form solution and prior work hasn't actually proposed a closed form solution, they have to use numerical methods to actually solve this. Since we have a closed form solution, again, it can be implemented very easily on smart devices. The other good thing is everyone contributes, which may not be the case in auctions. Right? So the strategy is kind of oblivious to it. In other words, our solution is agnostic to how many people contribute. Right? There's prior work that has shown that as the number of competitors increases, it kind of creates some disincentive for others to contribute, right? Which is not what we have in our setting. And a side effect of that, maybe if that's the case, you might actually see contributors trying to spread the word. Right? So if you tell other people to contribute, it's not going to affect your chance of winning. Right? So that might kind of motivate you to spread the word. So very quick look at performance. So the first thing we did was set up a benchmark. Right? I talked about how there is no actual optimization of the conventional two-log contest. So this is the first thing we did. So we could compare ourselves against a stronger benchmark. Again, I'm not going to go through the formulation. I'll just point out that the cost here is fixed, unlike in our case. Okay. And then we again propose a strategy, which you see there. So this shows you the optimal profit versus price curve for this benchmark. Okay, this is not for our scheme, but for the benchmark, as you see, with different valuations of the effort. And you'll see that this concave shape implies there is actually an optimal point, which is of course the peak of those curves. This is all solved using numeric methods, by the way. And you'll actually see, if you look at the optimal points, they actually fall on a straight line. Okay, that purple line that you see through the peaks. Okay, now to evaluate this, we looked at two setups. So as before, there's a two-player case and there's an n-player case. I won't get into the setup details, it's very similar to the prior work. This shows you the strategy versus the cost incurred. Right? The cost, the higher the cost, the more effort the agent has to put in order to contribute the effort. So as a result, you'll notice the strategy reduces, but you'll see our scheme is much better than the optimal benchmark, irrespective of the value assigned to the effort. So higher revenue and also higher cost. Right? The price is also linear, right? Whereas here it's constant. However, that doesn't tell us what's happening with the profit, right? Because the revenue increases, but the cost also increases. So does that mean the profit stays the same? Well, luckily it doesn't, right? So here you see the maximum profit as a function of the valuation of the contribution, and you very clearly see that the optimal scheme that we've proposed is 3 to 5 times better than the benchmark. And surprisingly, when you look at it from the point of view of the players, right? So that's from the point of view of the crowdsourcer, but the players also benefit. Right? So here you see the social welfare is about 7 to 9 times better than the benchmark. Okay? So this is kind of what we call a win-win situation. We also looked at the end player case where we looked at 2 groups of populations with different costs, as you see there, where population 2 is more diverse than population 1. I won't show you the results here, but just point out that we found that the profit for the second group of the second type was greater than the first type, and so was the social welfare. Right, so which means if there is actually diversity in the group of people contributing, it is beneficial to both the organizer and also the player. Okay, so to summarize, this is the first attempt at using this model of tulip contests. We set up an incentive mechanism and show how you can maximize the profit. We also have this the benchmark that is useful, I guess, for other researchers as well, and we demonstrate better performance. Right? So you always have a chance to win, so please contribute there. Okay, so looking to the future, where is this already? Well, we could look at richer models, so something like randomized auctions. Legal mentioned having multiple prizes, so that's something that we could also look at. Multiple rounds of auctions could be another way to move forward. And there are some very interesting intersections with things like trust, quality, privacy. So to get that going, we also have a paper where we look at both trust and incentives. And we have this concept of creating a web. Okay? And this is based on social relationships that we have. So this work was published in CCon last year. If you're interested, I can point you to that. And of course, by all means, all of this is purely theoretical at this point. And we are currently looking at how to do some actual experiments and practical evaluations. So yeah, before I end, a very shameless plug. At UNSW, we have 3 positions open at the moment in our school. Right? So if you're interested, please go and have a look. There's one on visualization, one on cybersecurity, and one in data science. Okay. And with that, I thank you again for sitting here rather than sitting in the beach. Any questions?
Yeah, time for a question or two. I have a question. So you approach it from the point of view of the crowdsourcer. As a user, how would your model be useful? Can I decide on the game that I should play based on?
Right. So I mean, once the game is set up, right? So it's like, okay, I've set up the game, and then now as a user, you're taking part in the game. So those strategies that we have are actually how you can gain best from this setting. Right? So once you know the setting, this is the best way you can benefit from this setting. So that's how it can be sort of implemented.
So if multiple users try to adopt that strategy, does it counteract your model?
No, actually it doesn't. That's what this that OPT, the first result is actually, that even if you have different kind of users, your strategy is the same as mine. Right? So that's the new result that we have.
Yeah. I was wondering that, you have mentioned like one dimension about that there is some like bidding process, although, there could be, like 1 minute or could be like multiple minutes using no second bidder. But what about, a scenario in which, if you are getting acquainted with like crowdsourcing, or if you're like benefiting from it, then you have to contribute to it. Like these kind of ideas, are you aware of kind of that?
Yeah, so here we do not sort of, since you're talking of closing the loop, right? So once you have the data, is that correct, my interpretation? That how can you collectively now make use of
Yeah,
this
so
data?
it means that, if you're benefiting it, then you have to contribute to it, otherwise you won't be able to.
Yes. So, yeah, that's,
So like,
sorry.
yeah, sorry.
Yeah, that's a good point, but here, in our setting, we are setting this up purely as a monetary incentive. So what we are talking of is extrinsic incentive, right? So all this work is purely on the extrinsic side, not factoring in that intrinsic motivation at all.
How do you improve the quality of data in the model?
Yeah, I don't have an answer. That's something we are looking at yet.
That is also very
Yeah,
important.
that I agree completely. That's we haven't yet looked at that and how it can become.
Right, looks like there are no questions, but before we conclude, we award this plaque to Salil. It says, association is hereby awarded to Salil Kanhere in recognition of your valued services and contributions to the success of the conference as the keynote speaker for WLN workshop.
Thank you very much.